share. All right, as I mentioned in this class, let's talk about the composite material extrusion. So you have learned what is the material extrusion and specifically the process of fused deposition modeling. So the composite material extrusion is one variation of the original material extrusion. So as you might know, even before the 3D printing, there were methods to produce the composite parts. As you can see on this page, we have different methods to combine the composite material with the polymer matrix. Basically, here shows a manual layup. So a substrate, a base shape is produced, and the material for the base shape is some like nylon or other thermoplastic, and then the composite material is glued onto this substrate. So that's the manual layup. Also, there's a way to basically it's like you have a plastic. The composite material is like a plastic bag, and you could manually spread the composite material as well as putting some the bonding fusion, bonding agents to attach the composite material onto other surfaces. Also, there are some automated fiber placement methods. As you can see here, this is the some composite fibers, and that is heated up and attached onto this substrate. This probably some thermoplastic substrate. So these are all existing ways to embed the composite material into the polymer matrix. Let's take a look at this video. Here it shows a in situ thermoplastic composite automated fiber placement. As you can see here, this probably some turbulent, turbine blade, something, and it requires really high tensile stress. So that's why the composite material is required to improve its tensile stress. And here is a robot. It is placing the some fibers, composite fibers, onto the thermoplastic substrate, probably nylon, I would say. And that's one example of the automated composite fiber placement. Let's go further. Also, let's take a little more check on this auto fiber placement. First of all, there's a little freedom to orient the fibers. Because we are in the previous video, there was a robot right? So it could have some orientation change when you place the fiber onto the substrate. Also, the geometry of the part is much simpler. Basically, what you will see is relatively flat, and although there's little curve, but the curve is more is not that much compared to the geometry we have in many 3D printing parts. So also this kind of part requires a core there, and that is the substrate, which could be the basis for the fiber to be placed onto. Therefore, this kind of method is not suitable for the bulk composite components. So that will be quite difficult. So as you can see here, this is the kind of parts which are applicable using the auto fiber placement, right? Basically, it has there's a core there, but still it's not a bulk part. Means, see, these are all hollowed region. But how about you have some solid part, some bulk part like this, right? And let's say you want to reinforce this part using the composite fiber. So there's no way to embed them inside this region using the what you have seen in the video, the robot automated fiber placement. So in that sense, this kind of part is still a challenge for the traditional, conventional automated fiber placement. That's why people are thinking of utilizing the additive manufacturing or 3D printing. So what they could do is, one possible way is, well, how about we print the core for the fiber using additive, because there are freedom in the complexity of the geometry using additive. So that suggests a good way to produce the core for the fiber reinforcement parts. And also, if you use some special material which could be washed away, which could be melt in some solution, that will definitely a good way to produce those shell structures. So, for example, the Stratasys could produce those wash away cores, and when after you print it, it could serve as the substrate for the for the fiber reinforcement. And after the fiber are placed onto this core, it could be melted if you dip it into the solutions, right? That would be really nice way to produce cores with more complex geometry. Other possibility for the cores is, well, instead of wash it out, you could break it away. So that's another possibilities. Basically, you could manually remove this core after the fiber are routed onto this core. On the other hand, there are some other cores, which is the structural cores. So for this kind of core, you want to keep them, because these structural cores will serve as part of the improvement of the mechanical properties, meaning it will improve the strength or some of the other mechanical property of the parts. And definitely you want to keep it instead of wash them out or break them away. And in that is actually what I want to emphasize on, and that's a very interesting research direction, and people are looking at it. So another good thing for this structural core is it hollows the interior of a part. In that sense, it will take out the material which are not necessary. it turns out to reduce the weight of the parts. On the other hand, it even improve the mechanical property of the parts. So that is why this kind of structural printing becomes a really, I would say, hot area in additive manufacturing. Remember, the weight is critical in many applications, especially the aerospace and astronautics applications, right? So that's why I want to emphasize on this. So any questions? Okay. Here shows you some of the examples. So this is called, I mean, this kind of structure here and here. This is one structural material. People usually call them the engineered lattice structures. So basically, this kind of structure is alternative to the honeycomb course. And it also has different ways, different shapes. And for different shapes, for different, basically, if you look at the two figures, you will realize, well, it's kind of a, these structures has a unicell, which is the basic unit of a shape. And it repeats itself to fill the whole space. So that suggests a very convenient usage of such kind of unicell. That is, when you design it, what you want to do is you want to figure out a way and repeat this unicell. And of course, you want to fill the whole space, interior of the parts. But you don't need to worry about the connection and also the transition of the parts, because this kind of unicell, it repeats itself, as well as its structure is fixed. The connection between each of these cells is also fixed. So you don't need to worry about whether one cell could be connected to another one. And that's the beauty of such kind of engineered lattice structure and the unicells. As you can see, there could be many different unicells in geometry. And here shows you some of the well-studied ones. And these could be all utilized in the additive manufacturing process to produce. You can never manufacture them using the traditional manufacturing methods other than additive. So that's kind of I always call it a good marriage, right? So this kind of unicell has a unique geometry, complex geometry. On the other hand, it has a lightweight, a good mechanical property, right? All good properties. On the other hand, additive has the capacity to produce complex geometry. So combine the two together, basically it empowers the capacity of manufacturing to make the part with less weight, less material consumption. On the other hand, has a really good mechanical property. Right? So let's take a look at this example. As you can see here, with this lattice structure, and we can conduct some tensor test. So what you can see from this figure, basically it suggests the relationship between the strain and the stress. And it presents a really nice strain-stress ratio, meaning it bears a large amount of stress compared to those, even compared to those solid shape. So that is what we desire, right? Just imagine if you have your some of the parts on the airplane replaced using such kind of parts, because there are a lot of hollow regions, so the weight are reduced. On the other hand, it bears even more load, more stress. So that will be the perfect case. Of course, this kind of mechanical property are governed by many aspects as well. As I mentioned, the different geometry of the unit cell could give you different mechanical property. Also, the strut diameter or shape, meaning this one. Can you see it? Right? If it has a thicker diameter, it could give you different mechanical property. I mean, in general, thicker diameter will present better mechanical property. Also, the shape of this diameter. Here it shows a I-beam, right? It's a kind of a square diameter. So how about a round cross section, right? That will also change the mechanical property. Another thing is the strut angle. That is this angle, and so on and so forth. So these are all variables, design variables, when you design this unit cell to fill the interior of your part. That will affect the mechanical property as well. There are some papers, as you can see here. Basically, in this paper, these different parameters are discussed with respect to the mechanical properties. If you have interest, you can look at it. This is a paper from my colleague, Dennis Cormier, and published in 2012. All right. So as I mentioned, to produce such kind of composite material and also the engineered lattice structure, so researchers are developing the extrusion-based method and add the composite material in it. So what you could do is first you print some thermoplastic as the filaments. I mean as the substrate. So these different materials could be utilized as the substrate, right? And they are mostly amorphous. And once this substrate is printed, the carbon fiber or other fiber, glass fiber, will be added to the substrate. There are different ways for the fiber. There could be chopped fibers or continuous fibers. So for the chopped fiber, basically you won't have a complete, sorry, a line of a fiber. Instead, you will have segments of the fiber, and this fiber will be embedded into this thermoplastic substrate, following certain orientation. Instead, you could also embed a continuous fiber into the parts. Continuous fiber here means, well, you really have a line of fiber, and that will be embedded into the substrate thermoplastic. And there could be variations for the continuous fibers like carbon fiber, glass fiber, or even Kevlar fiber. And these, I mean, as you might know, these are these have very good tensile stress. So it turns out it will improve the tensile stress of the parts with them embedded, right? And here shows I would say, a basic concept for such kind of printer. As you can see here, there are multiple printing head here. And accordingly, there will be different material go into this printing head. Some material will be the thermoplastic, and that will be printed as the substrate. And some of them will be the material will be the fibers, and that will be embedded into this substrate. So these two printing head will work alternatively. Means you print some substrate and then embed the some composite fibers, and then you have more thermoplastic substrate printed to cover those composite fibers, and so on and so forth. So it turns out you will have some result like this. So the major part are substrates, but in some regions there are the composite fibers embedded there. So these these shows the basic concept of the composite extrusion-based composite additive manufacturing, which is really simple, right? But any questions so far? Okay, let's take a look at the details. So as I mentioned, for the composite composite fiber embedding, there are different ways. One simple way is the chopped fiber. That means you have little segments of the composite fiber embedded into the substrate. Then a question is how you gonna place the fiber in the substrate material. And it turns out the alignment of the embedded fiber will be the critical aspects. As you can see here, this figure actually from a real print. As you can see here, this kind of spiral shape, right? And it turns out if you take a kind of basically you just look at the interior of this shape and check the orientation or the alignment of the fiber, you will see it apparently this fiber follows the printing direction, follows the motion of the nozzle. And that's how this kind of process place the fiber, that is, follows the motion of the nozzle. And this is actually preferred because if you look at the mechanical property of the printed part, if the chopped fiber follows the printing direction, and if you also set up the printing direction of your part properly, turns out you will have a part with the maximum mechanical property improved. So that's a very interesting aspect you want to keep in mind, because if you have a parts which you really want to have certain like tensile strength improve along certain direction, and probably you want to print the printing nozzle follows that direction to move, such that the fiber, the chopped fiber will be placed along that direction as well, and that will maximum the improvement of the tensile stress. I will show you some example later, but just keep this in mind at this moment, all right? And as you can see here, how could the printing happen for the chopped fibers? So there are some limitation for the process as well, because you are kind of blending those chopped fiber into some thermoplastic material. That means, well, you couldn't put too much inside it. Usually it has 10 to 15 volumetric ratio compared to the substrate, compared to the, I mean, the overall material volumes. And another thing is you need to consider about the nozzle jetting, because this kind of fiber, which sorry, has a have a really large friction. If you have a if you put too much composite fiber into the material, it turns out it will jam the nozzle. That's why it is restricted. You only put very low percentage of the fibers. And turns out that will also helps you to realize this process. Another restriction for the fiber is you want to have the the carbon fiber, I mean the composite fiber, to be placed uniformly, right? You don't want to have a region with too much fibers, and in some other region there are no fibers at all. So that's also a challenge, and that also suggests a proper percentage of the fiber to be blended into the material, and that's another thing you want to keep in mind. Also, the voids, the gaps, is critical as well. So the purpose for you to embed the composite fiber into the part is to improve the mechanical property. Yeah, if there is voids or gaps in the printed part, actually it will decrease the mechanical property significantly. So how to make the material, two different material bonded correctly, properly, that's another critical aspects when printing the material. And again, that will affect the decision to put how much composite material into the substrate. So these details we will talk about in the later slides. All right. Another very important concept is the critical fiber length. So how to understand this critical fiber length? That is, basically you are putting the material, the chopped fiber or chopped composite fiber into the substrate material. So how long is the chopped segment of the fiber? That is actually a variable, right? You could make it longer or shorter, right? But there is one restriction, that is this critical fiber length. So how to define it? If this fiber length is less than this critical fiber length, then fibers will pull out of the matrix rather than breaking. So that means, I mean, intuitively you can think of, okay, if the length of the fiber is too small, you are actually the fiber has no use. Basically, you are still breaking, you are still pulling the thermoplastic material instead of having the carbon fiber, I mean the composite fiber to improve the material property. So definitely you don't want to have your chopped carbon fiber segment has a too short length. And that's why we want to decide this critical fiber length. Does it make sense to you?
Yes.
Okay, good, good. Yeah, I mean that because if you think of this intuitively, it's quite easy to understand, right? Also, and let's look at this equation. Basically, it by doing this computation, you will have the critical fiber length. And as you can see here, this length is, is equivalent to this. And here you have the tensile stress, tensile strength of the fiber, right? And you have the diameter here. And on the denominator, you have the shear strength of the bond between the matrix of the fiber, right? And by combining them together, you will have the critical fiber length, right? So again, let's think of this intuitively. Imagine if you have the tensile strength of the fiber, which is really big. That means, well, you will have a really good, you will have a really long critical fiber length, right? You don't want to make your chopped fiber segment too short, right? And similarly, if the diameter is big, that will also increase the critical fiber length, right? On the other hand, if we look at this, the shear strength of bonding, that is how easy, or so that suggests how easy this carbon fiber to be bonded with the plastic. If it is larger, that means this will become, if this is larger, means it is easier for the carbon fiber segment, for the composite fiber segment bonded with the thermoplastic. So that means, well, you could probably reduce a little bit the critical fiber length. But it is smaller. If it is smaller, that means it's really hard for the composite fiber bonded to the substrate thermoplastic. That means it's better. You'd better increase the critical fiber length. So by intuitively thinking about this, you will understand how these work together. Any question so far? Makes sense, right? Good. And also, if you have fibers placed in the material, that could be different. That could be different situations. For example, if if the part has a tensile axis like this, so like the part like this. So this is the tensile axis. That means, well, you probably pull the part along this axis, or compress the part along this axis. And if you place this composite fiber also along this axis, so that will give you a equation like this to compute the overall stiffness of the parts. So as you can see here, EM and ER are the elastic modulus of the composite and the matrix. Basically, Actually, let me check. Okay, so this EM is the elastic modulus of substrate material, and this ER is the elastic modulus of the fiber, and this EC are the overall elastic modules by combining the two material together. And here are two coefficients, Fm and Fr. So basically, it shows the volume fraction. That means, well, let's see, the substrate material have 80% 80% in terms of the volume with respect to the overall volume. So then you have point A as Fm. And let's see if this fiber material only have 0.2, 20% volume with respect to the overall volumes, then you have a 0.2 as the Fr. And this will be the weight combined with the elastic modulus of the two different material. And overall, you will have a elastic modulus for the composite material. Does it make sense to you? Any question regarding this? All right, I think it's easier, right? Okay, let's look at another one. That's different. Let's use this figure again. So here shows one example. That is, okay, this is the tensile axis, and this is the orientation of the fibers. So how about you flip the orientation of the fiber by 90 degrees? So let's see, that's still the tensile axis is in this direction, but the orientation of fiber is in this direction. You're placing the fiber in this way. So how you compute, again, this stiffness. So we have another equation showing here. This, as I mentioned, if you have, let's draw the figure like this. And this is the tensile axis, and this is the direction. Maybe I use a different color. Like this. All right. As you can see here, this still the tensile axis direction, but this blue line shows you are placing the fiber perpendicular to this tensile axis direction. Then to compute the stiffness, you have this equation. It's hard to understand, right? But if we look at this figure, that is basically it shows the relationship between the angle of the fiber and the tensile axis versus its elastic modulus. So if the angle is 0, that means, well, the fiber's orientation is same as the tensile axis. It has a largest maximum elastic modulus. If you tilt this orientation of the fiber and change it, and you will see a drop, right? And it turns out if you make it totally perpendicular to the fiber, if you make the fiber's orientation perpendicular to the tensile axis, orientation, you will have the lowest stiffness of your material. And that suggests a very important principle when you design your parts and determine how you print your part. That is, you want to always align your fiber with the tensile axis direction. So that's the principle you want to keep in mind. All right. Any other questions regarding this principle? Nope. So for example, if you have a blade like this, my question is how you want to orient your fiber. Then to answer this question, you want to know what will be the tensile axis, because for the blade, the tensile axis is all the way along this axis, right? And it could be obtained through the simulation and also the testing, right? That suggests, well, when you print this part, you always want to have your fiber orientation along this axis. Instead, you never want to print your part with those fibers placed in this way. So you can see this is a very good example to show how this will affect your design decision and how you will set up in the software. If, for example, if you want to print it in the Markforged, and in the Markforged, when you play with the software, you will know there's a way to change the orientation of the fiber, and you definitely want to make sure it is this kind of setup, but not this. All right. Okay. Let's move on. So as I mentioned, in this BAM process, the carbon fibers are utilized to reinforce the part and to compensate the warping and of the part due to the thermal expansion, right? And as you can see here, these are the material they utilized, the chopped fibers utilized in their facility. And here shows, I mean, you can clearly see the fibers are along this direction, right? And they could build really big objects like the car shown here. And it has a really good mechanical property. At the same time, the weight is light compared to the metal made cars, right? So since we talk about the direction of the tensile axis, in the previous example, this axis, the orientation is simple, right? It's almost a one unit direction. But in many parts, it's really hard to find a single direction. It is very complex for a part like this. How to tell its tensile axis direction? It's really hard to give you a uni direction, and that suggests a change in the manufacturing process. That means also in the design as well. That means you have to figure out some other curved direction of the tensile axis or the stresses, and that that is due to the anisotropic material property of this design, as well as the geometry itself. So I think we can stop here, and let's talk about the more general fiber placement and orientation in the next class. All right. Let's have like 10 minutes break. Go back at 11:10. All right. All right, let's continue. Just 1 second. Let me share my screen. So as I mentioned, it is not always easy to find out the stress orientation or the tensile axis in many cases. For example, like the one showing here. And you have your design like this. And this design is made of all this kind of complex cells. For this, it's really hard to tell where is the orientation of the tensile stress. In that sense, it is hard to tell the printer how the toolpath will look like. And one reason for this is the geometry of this design is complex, much more complex compared to what we had previously, the blade, right? Another one is the anisotropic material property of this part actually is a function of the part orientation. And that means if you print the part in different orientation, the mechanical property, the material property will be changed accordingly. And that will make things even more difficult. And that will make the toolpath planning really challenging, right? So that's how this kind of work requiring new thoughts on the toolpath planning. Actually, there are some methods introducing the finite element analysis for the fiber placement and orientation. Let's say you have a shape like this, an L shape, right? And here you want to fix it. And you have a load along this direction. Of course, you could do a finite element analysis and have this so-called stress field. And here show you some critical regions with a really large stress concentration. And it turns out this will help you to define what kind of direction of and the magnitude of the stress. So as I mentioned previously, you always want to follow the direction of the stress. And if you look at this, here shows you, well, you definitely want to follow the direction of these vectors. And these regions corresponding to here, these critical regions with a stress concentration. And basically that indicates in these regions, you want to reinforce the structure by embedding the fibers there, right? And the fibers orientation will follow the stress vectors. For this particular example, it seems there is a solution, right? That is follow the parts. I mean, follows the direction of these vectors to place your fibers. But that only works for the XY plane. So how about you have a part like this? I mean, it's really hard to have a direction only on X, Y plane. It's a space vector, 3D vector, and it's not a X, Y plane vector, right? That will complicate things. And but if we come back to an example like this, so let's say you already have such kind of fiber placement vector and in these directions, how are you going to utilize it? How are you going to print it during the printing process? So what essentially the printer do is something like this. So as you can see here, this is how the Markforged print with the fiber embedded. These black regions are the fibers, and these white regions are nylons. So if you have the stress vectors identified, and that is the fiber, also the fiber orientations, you can set it up in the software and follows these regions in each of the layers. And it turns out you will have the fibers to placed in the thermoplastic substrate. So that's how it works. But as I mentioned, it only works for the 2D cases. That is the stress field or the stress vector are on plane. And in that way, you could use the Markforged to print it. Does it make sense to you? Any question? Nope. And during the process, as I mentioned, there will be the nylon matrix printed first, and then the continuous fiber or chopped fibers will be embedded. If the continuous fiber is are embedded, there will be a cutter to cut once these fibers are embedded. For the chopped fibers, there's no such a process for the cutter, right? It depends, right? Also, the fiber's nozzle diameter will match the filament diameter as well. During the embedding of the continuous fiber, this fiber will be heated up to increase the bonding between the fiber material and the nylon matrix, such that you will have a close bonding. Okay. These are the aspects for Markforged machine. And here gives you the mechanical properties of the materials utilized in the Markforged. You can find it out on the Markforged website. Here are different fibers, like probably this carbon fiber and Kevlar and a glass fiber and so on and so forth. And this is the nylon, which is the substrate or the polymer matrix material. And you will need to look at this. And that could be possible for you to do little computation based on these numbers as well. All right. As I mentioned, the Markforged is able to provide the embedding of fibers, composite fibers, into the printing, but there are many limitations. First of all, the turning radius is very small. As you can see here, it does not support a large turning radius. That means a very curved trace, very curvy to the path cannot be utilized for the Markforged. There are restrictions when you use the software. Also, the efficiency compared to the conventional printing methods, which is the automated tape layup, it's much slower using the Markforged. Another drawback, as I mentioned, it only works for the 2D contour. That is, well, if you could figure out the fiber orientation in 2D, you could think of using the Markforged to print. So that only works for the 2D. All right. Also, for the software, it's rather a very closed system. I mean, indeed, there are not much to be released for you to play with. Basically, there are only quite a few options you could select or parameters you could input. There's no G-code interface to control the fiber deposition path. That means if you look at the Eager software, you will realize there are only a few options you could select, either this way or that way. And you cannot customize this tool path yourself. So that is a very restricted setup. I think this is a relative a new technology, and if it release the interface for you to change the path for the fiber deposition, that could cause the instability of the process. It could fail the printing. And for commercial manufacturer, they don't want to have this. The stability of their, I mean, reliability of their product is very important. So they just close up these interfaces and make sure the successful printing could be achieved for in the printing. And that's the payback you have to have a stable printer. If you ever use, I mean, if you play with the printer, you will realize it's compared to the fuse deposition machine, which is a very cheaper and also a more like DIY type machine. This is well tuned. I mean, the Markforged machine is well tuned. It's stable. And on the other hand, it has less to play with, less to change. All right? Mm-hmm. All right. This is another development, which is the direct wire embedding. And basically, it is a modification to an existing standard RipRap 3D printer, which is a open source 3D printer. And what it does is it embeds the heated copper wires into the thermoplastic basis. As you can see here, other than the thermoplastic material, it has the copper wires also. And similar to the Markforged, in Markforged, it embeds the composite fibers into the polymer matrix. In this case, this printer embed the copper wires into this substrate. I mean, quite similar, but you can see it's a quite preliminary result. There are manual operation as well. You have to cut the wire manually, right? That's just some trials of this process. Another interesting process is this this machine, and there is one challenge for the composite additive. That is the adhesion between the different layers. Basically, between layers, it lacks the polymer entanglement between those layers. especially for this formous thermoplastic materials. And that will, turns out, affect the mechanical property of your prints, make the strength and the stiffness of the prints inconsistent in many regions. So this company come up with a solution. Basically, they have the carbon nanotubes embedded into filaments. And as you can see here, these two are the CNT, the carbon nanotube. And then you have a layer of thermoplastic coated onto this carbon nanotube, and use them and fuse them together during the printing. Basically, the microwave energy are applied during the extrusion. So by doing so, it improves the interlayer adhesions. So I don't know if you have some understanding about the interlayer adhesions. That is, as I mentioned previously in I think in the first lecture or second, I don't remember, but for current additive, the material property, mechanical property in different direction are different. For the XY direction, it is in general is better, and for the Z, it is worse than the one in X and Y. The reason is we are printing the parts layer by layer along the Z direction. So in the X, Y direction, the material are bonded much better than the one in Z direction. So in the Z direction, each of the layer needs to bond it together. And this kind of interlayer adhesion or bonding are worse than the one in the XY direction. That is what it talks about here. It talks about here. That's the interlayer adhesion. So what this company does is kind of they make this kind of a new material and come up with this machine and process to fuse the different layer together. In that way, they improve the interlayer adhesions, and turns out to improve the mechanical property of the material of the parts in the Z direction. That's what it does. All right. Any question? Okay. Now let's talk about some new development, some cutting edge technology, which is under developed even at RIT in the Brinkmann lab, which is the non-planar deposition. We have a Titan robotics machine there, a giant machine there, and that is the platform for the non-planar deposition. We also have a machine set it up in the 3D printing lab as a corner near the other door, if you ever look at it. So that machine is also the non-planar deposition for the composite material. And let's take a good look at it. So the motivation for such a process is the challenge for the lattice structure composite extruded using the material extrusion. So let's say you have your lattice structure like this. If it is printed as a layer, what it will look like is something like this. Because these are very thin, right? These frames are quite thin. So it will, if you print it in layers, it will like you are adding dot one by one. So you can imagine the interlayer adhesion will be really poor because the contact area of each of the dots is really small. that will provide little adhesion. And also it is inefficient to print in layers, because even for such kind of thin frame, it will print first this dot and all other dots in the same layer, and then move to the second layer. I mean, of course, lift a little distance in the z direction and print this dot and the other dot, and so on and so forth. So I mean, if you look at this kind of shape, an immediate thought could come to your mind is, how about we directly extrude along the direction of this frame instead of printing them layer by layer, right? That will be a very straightforward thought. And that is actually what other researchers are looking at. And that is what we are also looking at RIT. Also, another drawback is the slope of the printing will be restricted. For example, for this, probably you can still successfully print, but something like this, that is, this angle is too small, and these regions could require support. And you are talking about printing a really thin frame like this, and still it requires support. So that's kind of I would say it doesn't make sense, right? So also that suggests, how about we just extrude along this direction instead of printing layer by layer? So any questions about this? Okay, good. Yeah, that's what people are doing. So this is so-called the axial lattice structures. And there's a company which is the Branch Technology. So they focus on the home constructions. So what they developed is this robot systems. And this robotic extrusion system is utilizing the chopped fiber reinforced thermoplastic filament. And the extrusion toolpath will follow the axis of the lattice. That is, if you have the frame like this, the extrusion will along these struts instead of printing them layer by layer. Also, you could orient the fiber in different orientation in the space. So when you print it, the fiber could follow the direction of these struts. So that's a really nice property. Because, as you can see here, it has a really giant robots printed here, and it apparently has some mobile capability, means it could move somehow. And that is possible to be utilized to produce some larger objects like these. And these shows the, I mean, these are the results, examples presented by the Branch Technology. As you can see, it has a room level objects built from their process, right? So there are little problems for this axial lattice printings. I mean, actually, these are the challenges for all kinds of axial lattice printing. So, for example, when you print, there could those frames, those struts, need to be cooled to stand, right? Otherwise, it will fall down. Then how you decide the way to cool the struts, and how you want cool the nozzle as well. That's the challenge you need to think about. Also during the printing process, because you're printing these one by one, right? There could be collisions between the nozzle and the previous printed structures. Remember in this process, there's no layer by layer printing. Previously for the layer by layer printing, for one layer, for the layer to be print, there's nothing. You could collide. The nozzle could collide. But for this one, you could build one frame, another frame, and then build the second frame. And because there are existed printed frame already there, there could be collision between the nozzle with these first printed structures. And let's take a look at these questions one by one, these challenges one by one. So as you can see, if you want to print those structures in an open space, that means if there's no support. So for example, if you have these filament printed, and then you want to print a strut like this. So what you want to do is, after you extrude this shape, you want to make this solidified as soon as possible, such that this will not fall down. Otherwise, it could be, if it is still soft, it will fall down, easily fall down due to the gravity, right? Due to the effect of gravity. So that's why that could be a solution by introducing this kind of cool coat air to blow on the printed structure and cool down the filament, such that when you print another portion, this become more solidified. Of course, after you print this, the cool air gun will be here again to cool it, to cool down these newly printed part, and so on and so forth. So that could be a solution for the printing. That is what I was talking about, the cooling, right? The cooling setup for the printing. Another one is the collisions, right? For example, if you want to print this kind of shape, that is not good to print them in one pass. That is, if you print in a continuous motion, it turns out you could have you could end up have some shape like this. So one more feasible solution would be you print one side of the struts, and then print another side, right? So that will give you a sharp turn instead of having such kind of curved shape. If you print it in a continuous motion, that is what exactly you have on these examples, right? And if you have a printing path like this, turns out you have a really nice sharp turns, sharp corners for the neighboring two struts. So that is, you print this axis first, and then print this one to join them together here. And turns out that's what you want to have. So these are other, sorry, this is another consideration you want to think about during design this process. And it turns out this is not the feasible way, and this is a feasible way. All right. Any question? All right. But one thing you want to think about is, what if you have this printer in the space, or on another planet, on Moon or Mars, Will this be improved? This kind of problem be improved? I mean, that's definitely possible because the gravity in the space or some other planet could be smaller, much smaller than the one we have on Earth. And it turns out it may become a feasible process. And that's another interesting angle to explore. Actually, there are some, actually we are working towards a research that is to print this kind of lightweight structure on Moon. And basically the idea is on Moon, if you are talking about to build some permanent like residency site, or for people to stay longer there, or even on Mars, right? You definitely want to have some automated machine to utilize the material on that planet to build the house or other facilities. And that suggests some of the efficient use of the material. That's why this kind of lattice structure could be a good candidate for building a home or a facility on Moon or Mars. And if that's the case, then you need to think about the physics on those planets instead of the one on Earth, right? And such kind of process will be explored as well. So it's ongoing. I mean, let's see. Another very interesting aspect is the collisions. So as I mentioned, these axes will be printed one by one in sequence, right? Let's say you have this printed and this printed right here. But you want to start here and print another shape like this. And it turns out you figure out the nozzle will have a collision with the pre-existing portion you printed previously. The reason is because the nozzle has a volume. It's not an ideal dots. It's not just a dots. It has such kind of volume. So it is not a it is sometimes it just cannot avoid collisions. So if you plan your path, first print this, and then print this, and then print another part, that could be the collision happens. If you start from here, you print this first, this is the first printed, and this is second printed, and this is third printed, and you start from here. And that's a start point, and that's the end point for printing this third strut. And that will be a collision between this and this. So that suggests you definitely want to optimize your sequence of printing such that there will not be a collision. And that's also a very interesting consideration for the toolpath. Another possible collision will be like this. Let's say you already have this portion printed, but you have another part print here. And when you move the nozzle towards this, there will be a collision between the nozzle and this existing part, just printed a few times before. And another case is, well, if you have a really tall, portion in your printing, and then you want to move your nozzle to some lower level, there will be collision between the nozzle and the part. So there are different, as you can see here, we actually list out the possible reasons for the collisions. One is the extruder angle. So if you have a more narrow, if you have some extruder like this, right? That could be avoided. Also, if you have a thinner extruder like this kind of collision could be avoided as well. Another thing is whether the height of the extruder, right? If you have this portion even higher like this, right? Then there's no collision at all. So that means the geometry of the extruder will greatly affect the collision, whether there will be a collision or not. So that suggests us when we do the toolpath planning, we need to consider all of these, and hopefully there could be some. I mean, ideally there should be some simulation for the collision before before this printing happens, right? And let's look at an example. See, you see the cold air gun to cool the material printed. So that's how it works. And you can see the sequence, right? It always starts from the lower level to the higher level, and to avoid possible collisions. If you print, also you print the interior part first and then the exterior. Just imagine if you print this portion first and then there's no way to print the interior. It's really hard, right? So you can see how the sequence of the printing affect the collisions, and also how those cold air cooling enables the printing as well. You can see a cubic shape is cubic lattice structure is printed, and you can see the even the exterior regions could be filled using the printing process. Any question? Very interesting process, right? Also, as I mentioned, the filament is aligned quite well during the printing process. If you have a zoom in view on this portion of the parts, you can see roughly it follows the direction of this axis, right? You can tell it's something like this, and here is something like this. That suggests a really nice mechanical property. It suggests the optimization of the alignment of fiber in the part. So if compare the printed part with the traditional fused deposition modeling, with respect to its with respect to the mechanical property, you can tell how good it is. Actually, it is time. I'm sorry about it. I made a mistake. It's the time. If you use the axial lattice extrusion, also versus the fused deposition modeling, for printing two parts. One is 3 by 3 by 1 lattice. Another one is a 3 by 3 by 3 lattice. You can tell how the efficiency of the printing achieved compare for the one printing using the axial lattice extrusion versus the traditional fuse deposition modeling extrusion. And the efficiency improvement is also significant in spite of the mechanical property improvement. All right. Any questions? I think we have complete the composite printing part. Any questions overall in this composite printing? No? I think I want to stop here since we complete a module. And for next class, let's talk about some of the geometric modeling and computation for the 3D printing, including the layer generation, as well as some computation about the printing speed. Also the infield patterns, how the infield patterns could be generated, how to compute those paths. So let's stop our class here. Again, the deadline of the homework one is today's 10 p.m., right? So be sure to submit it on time. Otherwise, there could be some penalty deducted, penalty points deducted. Also, I will explain the answer in next week's class. So be sure to submit it definitely on time. All right. So this is end of the class.
Thank you, Professor. Take
Yep.
care.
Thank you, Professor. Have a good week.
Yeah, you too.
Thank you, Dr. Sean.
Yep. See you guys.